Hey everyone, welcome to the first episode of Chemistry for Your Life. I'm so excited. I'm Melissa. I am a master's of chemistry, and I am currently still in school for trying to get my PhD in chemistry, which I question every day. You should probably cut that out. I'm trying to get my PhD in chemistry, and I absolutely love chemistry. And all I want to do with my life is to share that with people and make it accessible to people. And that's part of what this podcast is.
And I am Jam, and I do not know anything about chemistry. I like science, but more of what I bring to this podcast is questions, because I want to understand, and also podcast experience, because I have another podcast called Podcast for Your Life. That
shameless plug.
Shameless plug. But within the For Your Life family, this is a much more educational, much more learning podcast, whereas the other one is not at all that way. So I'm excited to get to learn about chemistry with you guys as listeners.
Woo! Yeah, chemistry. Okay, so the overall objective of this podcast is just to talk about the chemistry of your everyday life. There's chemistry all around us, and I found that there are a lot of people in my life who think chemistry is scary or boring or doesn't apply to them or they can't understand it. And what I found is just that that's not true. There is chemistry everywhere. It's easy to understand if you have the right teacher, or worth it to take the time to understand. And it's not scary. It's really cool. But I think you need someone to sort of help you see that.
Yeah.
I had a really good high school teacher that did that for me, that started opening that door. So
I guess I'm predisposed to like science and want to like it. So maybe I'm not representing every listener. So I'm biased a little bit already, but I do want to understand it. So I'm not coming with like assuming it already makes sense, that kind of thing. So
yeah. Okay, so today we're going to talk about how soap works. And this one is one that I love to tell people when I see soap bubbles flying around. I'm doing dishes and my roommates are nearby. But before we start about that, I do want to say something. So technically I'm, quote, an expert of chemistry. I have a master's degree in it. That makes me qualified to talk about it to some extent. I'm working towards a PhD in it. But I think what I thought before I was an expert, and what not lots of non-chemistry experts think, is that chemistry experts know everything about chemistry, but it's not true at all.
Yeah.
So there are going to be a lot of times I have to say, I don't know, or I think, or my best guess is this. And I just want everyone to know that an expert doesn't mean I know everything. It almost means that I know more of how much I don't know.
Right. Yeah.
But it does not mean that I know everything. So I'm not going to be I won't know all the things.
Yeah.
Not the guru.
Yeah, that makes sense.
Great. Okay, so how soap works. Okay, so when I'm talking about soap specifically, I'm not talking about antibacterial or any of that right now, because I'm not a biologist of any sort. But I'm talking about like dish soap, grease soap, soap that gets your oily pan clean or whatever. So before we talk about soap, though, we have to talk about bonds. And before we talk about bonds, we have to talk about atoms.
Okay.
How much do you know about atoms?
Okay, here's what I know. So atoms are like the smallest, like, I guess they're not the smallest because they're made up of other particles. But basically the idea seems to me that like everything is made up of atoms that are somehow stuck together.
Yes.
In some way. So like the table that all our stuff is on, it's like all pretty similar, a lot of pretty similar atoms, maybe like a makeup of different things because this is a plastic table, so maybe it's got a lot of stuff going on in there. But essentially they're stuck together, and they also are forming a solid, which allows us to put stuff on top of them. And there's protons, neutrons, and electrons in an atom. And electrons are revolving around, sort of.
Okay,
like
that revolving around. So everything you said was true. That's a really good understanding of atoms. But the revolving around model that you've seen, it's like the thing at the center and then like the orbits around it, like what you see on Big Bang, or they put it on like makeup bags and stuff. That's not a really good representation of an atom, actually. So it does have a positive center. It's got neutrons and protons at the center.
And those are like, I remember seeing that diagram where they're like, they made one of them one color, one of them the other. So they're kind of like a ball, then they're stuck together.
Yeah.
Okay.
So those are at the center.
Okay.
Like pretty close together, stuck in together, like make a fist, or that's the center.
Okay.
Then all around the center, so imagine you've like got your center and then there's a cloud around it of electrons.
Cloud.
Basically.
I have heard that since being in like school, like grade school or whatever.
Yes.
That it's more like a cloud than it is like, okay, yeah. I think I had heard that, but when I was taught it as like a layman, it was orbiting or whatever.
Yeah, so they don't have a specific orbit, but they do sort of hang out around the positive center. And electrons are negative.
Okay.
So it's like you've got a negative cloud floating. It's got some specific shapes that it tends to take. That doesn't really matter for this conversation. But you've got a negative cloud of electrons sort of surrounding a positive center.
Okay.
Okay, so that's an atom. Okay, so we need to talk about bonds. To talk about that, we've got to talk about atoms.
Okay.
So each atom has its own unique ability to pull the electrons closer to it.
Okay.
That's called electronegativity. So its ability to pull the electrons to it varies from atom to atom.
Okay.
Okay. So two atoms that share electrons is a bond.
Okay. So those, meaning like those atoms get like kind of stuck together? Mm-hmm. Okay.
So, and I think of it almost as they're holding hands. So there's an ideal number of electrons that each atom wants to have around it.
Okay.
So carbon wants 8, right?
Okay.
So if it doesn't quite have 8, it can bond with other things to add up to 8
Okay.
of its electrons. That part doesn't really matter a ton for this. It's more that just that they share electrons as a bond.
Cool. 'Cause I was going to say, like, I have a lot of not confidence about my understanding of that. But as long as I know that they want to share electrons, that they don't have the number that they want.
Right.
That's why they stick together.
Mm-hmm. They stick together because basically they want to have an ideal number of electrons in their outer shell.
Okay.
So they get their ideal number of electrons by sharing electrons between each other, and that's what holds them nearby one another.
And sharing is caring, so we know that that's true even at the atomic level.
Yes.
Okay.
Sharing is caring. And there are different types of bonds. The kind I'm describing to you is a covalent bond. It doesn't really matter what other bonds there are for the purpose of our conversation today.
Okay. Sweet.
But this type of bond is what we're looking at today.
Okay.
So the electrons are shared between two atoms.
Okay.
And if those two atoms have the same amount of electronegativity, so the same ability to pull electrons towards it, if they have the same ability to pull electrons towards it, then those electrons will be perfectly evenly shared between the two. It's a totally neutral bond with two positive centers and a uniform electron density around it.
Okay.
So a good example of that is nitrogen. Nitrogen is usually actually in the Earth's atmosphere as N2.
Okay.
Two nitrogens bonded together. They have the same electronegativity because they're the same type of atom, and so it's just all equally shared between the two.
Okay.
Okay. So in the tug of war of pulling for the electrons, they have the exact equal amount of strength.
Okay.
Okay. Sometimes two atoms with very different electronegativities will try to share electrons.
Okay.
When that happens, the one that's better at pulling the electrons towards it, the one with more electronegativity, will get more of the electron cloud on its side of the bond, leaving the other side of the bond more positive exposed and not covered by negatives.
Okay.
You look like you have questions.
Well, I sort of do. I think I'm not getting it quite yet, but so it sounds like it's out of balance in some way.
Yes.
Okay. Is that the main thing I should take away from that?
Yes.
Okay.
So there's the perfectly neutral, evenly shared bonds that are totally in balance. And then there's bonds that aren't that way, where part of the bond has a higher concentration of electrons and is therefore slightly more negative.
Okay.
And the other part of the bond has an absence of electrons, making it more positive.
Does that make it to where they have less strong of a connection anyway? Like the other ones that were like equal, had equal desire for electrons and like made a really good pair. How does that affect their like ability to stick together, so to speak?
I think their stick togetherness. So that's an interesting question. I'm not sure I can answer that off the top of my head. I might be able to go
so I don't know.
Look into it. It's not super relevant because we're not breaking bonds with soap.
Okay.
But we just need to know that there's the unequal pull of the tug of war.
Okay. Tug of war. Got it.
So the question you're asking is more about how the bonds would break and the energy it would take to break the bonds, the stick togetherness, we don't really need to get into that.
Okay, sweet.
It's a good question.
So in soap, it's a little bit out of balance, is what you're...
No, you're jumping way ahead.
I'm trying to get my like my tangent back on, but now I have, but I haven't.
You have not successfully, and you've not successfully seen where this is going. Okay, so let's go back on our roadmap and make sure you're tracking with me. So we know about atoms. We know that each atom has a different ability to pull the cloud of electrons towards itself.
Yes.
And then atoms will share electrons.
Yep.
And sometimes they'll share them perfectly evenly between the two. And when they share them perfectly evenly between the two, there's not a negative or a positive side.
Okay.
That's called a nonpolar bond.
Okay.
Then the other kind of bond we were talking about, where the electron density will be pulled more to one side than the other, that's called a polar bond.
Got it. So one is positive, or one's more positive, one's more negative.
Yes. So usually...
Like a magnet?
Exactly like a magnet.
Got it.
That's exactly right.
Okay.
So there's a partial positive we call and a partial negative. It's not as if all the electrons are on that side and it's negatively charged, but it just has more negative on one side and more positive on the other.
Okay.
And the reason for the positive is basically there's an atom that's lost some electron density around it. So that positive center is almost shining through.
The protons and neutrons that are part of that atom are less...
surrounded.
Yeah, okay. There's less negative to make their positive negative.
To make their positive neutral.
Neutral.
Yeah.
Got it. Okay.
Yeah.
Sweet.
Okay, so those are the two type of bonds, polar and nonpolar.
Got it.
Okay, so this is where we get into everyday life of things around us.
Okay.
Polar bonds and nonpolar bonds. If you have a polar bond on a molecule and a nonpolar bond on a molecule, they're not going to interact with each other.
Okay.
Nonpolar bonds like to interact with other nonpolar bonds.
Okay.
So they'll sort of stick together. Polar bonds like to interact with other polar bonds. They'll sort of stick together.
Okay.
So have you ever seen oil float on water?
Yes, I have.
And that shiny rainbow, if you see oil in the parking lot on water, that's because the oil and the water aren't mixing.
Yeah.
Can you guess why?
Because one is polar and one is not?
Yes.
Okay. I was like, yes.
Do you have a guess about which one's polar and which one's not polar?
I have heard that, this is like weird because I think a lot of times I'm reaching back into like learning from even like middle school and high school. And who knows how many misunderstandings are there because I didn't ask a question in class or because I just misremembering.
Yeah.
But for some reason, I have a memory that water is polar.
That's exactly right.
Okay, cool. And that oil, I guess, in this case, isn't? I mean, like...
Oil is almost always nonpolar.
Okay, sweet.
Okay, and in my experience, most nonpolar things have an oily feel to them. Ideally, you don't just stick your fingers in things in the lab, but every once in a while, maybe I got something really nonpolar on my fingers, and it has that oily feel to it.
Oh, that actually kind of makes sense to me now because, like, water... Like you can like shake it off your hand easy. Like it's just gonna stick together in a droplet, and then you can be like, all right, or like just try that off.
Yeah.
But oil likes to like not stick together to itself.
Yes.
And like it's so evident, even like in a drop. If you do a drop
of oil, I think it's not that it doesn't like to stick together to itself. I think it's that you have. This is speculation.
Okay.
I think it's that you have oils on your fingers, and the oil that you get on your hand sticks to the oils on your fingers.
Oh, got it.
You don't usually have water as part of your skin,
right?
I mean,
I guess we do have water, but like. Yeah, it always seems like even just visibly, like the water wants to be its one like droplet thing and hold on to itself.
Because there's natural oils on your skin and the water doesn't adhere to those oils.
Right.
Okay, so that what you're coming up into is a chemistry. I don't know if it's really a theory or a law or anything, but we just say like dissolves like.
Okay.
So things that have like bonds or similar bonds will dissolve each other.
Okay.
Okay. And there's other types of bonds in water besides polar bonds. There's a special type called hydrogen bond. We don't really need to talk about that for understanding soap. It's not important. Just knowing that there are different types of bonds and that similar bonds like to dissolve other similar bonds.
Okay.
So water and oil don't mix.
Yes.
Because of that. So here's the thing, though. If water and oil don't mix and you have a dirty pan and you're trying to clean it, it seems like the only other option is to get more oil on it to make it go away. But then there's still oil on your pan.
Right. Yeah. That's weird. I've never really thought about it. I just know that water on its own doesn't really do anything. It just like skates right over it.
Skates right over it.
So, yeah, it's pretty annoying.
Okay, so what soap does that's so incredible to me. And it's even more incredible that they figured this out without knowing on a molecular reason why.
Mm-hmm.
So I think they used soap long before they knew the molecular reasoning behind why it works.
Uh-huh.
But soap is a molecule that has one really long non-polar chain.
Uh-huh.
So almost like an oily type chain.
Yes.
And at the very end of that chain is a special group of atoms.
Okay.
It's called the functional group.
Mm-hmm.
And that group is very polar.
Okay.
So soap is made up of a non-polar portion attached to a polar portion.
Oh, that is weird.
It is weird.
Don't people make soap out of like fat and stuff?
Fat and also sodium hydroxide or lye or base, which causes the chemical reaction that makes that functional group.
So it's not just like it's this natural occurring thing.
No.
It has to have been mixed with something. Because like, it makes sense to me that there's the oil likeness. So I've got to use some sort of oil to get oil off. Mm-hmm. And I've heard that it's made from fat, but then I'm like, yeah, I can't just take some animal fat and just like scrub it all over my pan.
No, you can't.
That sounds
I mean, you
pretty
can
gross.
do that. I think that's the theory behind cast iron pans. But
Oh, okay.
yeah, so it's animal fat mixed with sodium hydroxide that has usually in heat, and the chemical reaction takes place. So we have students actually make soap in labs almost every semester. I'm trying to think. I've taught a lot of different ones. We definitely did it in Gen Chem for non-majors because it's just really cool for them to see soap.
Yeah.
And literally what they did was take vegetable oil and a base, maybe something else I don't remember off the top of my head, and they just stirred it over heat until it became soap. And then they would take, after the reaction happened, they would take some out and put it in a vial and shake it up with water, and they would see the bubbles. They literally made their own soap.
Interesting.
Yeah.
Man, that would be fascinating.
It's really cool.
That's crazy. So basically it's like as simple as one thing is these things just need to be combined. Like there's this non-polar deal that's already part of like fat and oils.
Yeah.
And then if we can just get a little like polar thing on the end of that tail, then we've got some soap going.
Yes, exactly. And in situ, when soap is actually working, pretty much what happens is you'll get a bunch of soap molecules that surround a pocket of grease. And so all of the little non-polar tails surround it. All the non-polar tails are touching the oily part, leaving basically a sphere of the part that likes water all sticking out.
Okay.
So it totally covers your grease or your oil or your fat with the non-polar part, leaving the polar part sticking out and ready for the water to just come and wash it away.
Interesting. I've noticed sometimes, like this is kind of like, I just do this for fun. So if I have a pan that's got some grease on it, put like a little bit of water, and then you'll see that the grease usually kind of floats on top sometimes or whatever.
Yeah.
So I'll put a drop of soap, just one drop into that, and then like something immediately happens.
Yes.
Like it's like a visual like,
Yeah.
and it looks like in movies when there's like some nuclear explosion that happens. It looks like that, but on this very tiny, way less significant scale. But it is still cool to watch. It's like the rainbowness kind of like just goes away.
Yeah.
And I've loved doing that for years and years, not knowing why, but it's just like a little bit, it makes doing dishes like a little more fun.
Yeah. And now you'll never be able to do that thing without thinking about how soap works on a molecular level.
Gosh, that is crazy. So is that all the way down? Do we get all the way down to the...
We got all the way down. So you learned about atoms, which make bonds, and those different types of bonds the different types of atoms can make. Cause polarity and non-polarity, and the way to bring polar things and non-polar things together is to have something that's a little bit of both.
Man, that's crazy. Okay, so what if we try this? What if we see if I understand it by me doing like the layman's version that summarizes all of that?
Okay.
And see if I get it or not.
I would
like,
love that.
Because like if I misunderstood something, we could correct it.
So now you teach me about how soap works.
Yes, which I've also heard that's like a thing that is like one of the theories in teaching is like teach a thing and then have people try to repeat it back in their own way or whatever. So commit something to memory. So there are atoms. Atoms like to stick together because of a lot of different reasons. But sometimes...
A lot of different reasons, mostly just wanting the right number of electrons.
Okay, wanting the right number of electrons. Sometimes they have the pleasure of that being a very mutual friendship with other atoms. Other times, it's a little bit not that way. Like when you have a friend who borrows more things than they let you borrow.
Yes, exactly.
You're
like
still friends, but you one of you is giving up more than the other most times. But it's totally fine. So when that happens, there's polarity, kind of like a magnet, because one thing is giving up more electrons than the other, and so it just means that there's like an imbalance.
Right.
But it's not like a magnet in that it's like this incredibly strong, like totally opposite. It's just that they have different negativity or whatever.
It's sort of like a spectrum. There can be slight differences or significant differences.
Okay. So things that are polar, like water, have stick together well, or whatever. And then things that are non-polar don't stick together well, or they don't have as much like.
Okay, you're close. Should I interrupt right now, or should I let you keep talking?
Maybe let me keep talking and then see if I
get the rest of it. Okay.
So things that are non-polar. Oh, dang it! This is harder than I expected.
It's harder than I expected on my end, too. I thought this was going to be so simple, and then I realized that I had to go all the way back to explaining atoms to be able to explain soap.
Because like in the situation of soap, you've got some grease on a thing. And that grease is non-polar. And you're putting water on it, and the water's polar. And so it's not doing anything because they don't really interact well. Like they can't just affect each other on their own because they're different.
Yes.
So that's why we see them separate. It's not that they're like hate each other. It's just that they don't have a way at the moment of interacting.
Right.
Something like that.
Yes.
Okay. And so soap is this magical thing that scientists figured out. I like saying scientists. It makes it sound like people in a room that are always like working on this stuff.
That's what scientists are. That's all we do. We only wear lab coats and stay in the lab.
Yeah, right. Because someone's got to figure this stuff out.
Right. They don't get to have lives.
So some person somewhere sometime figured out if they took some version of a non-polar, like oil or grease from an animal or whatever, and mixed it with something that is polar, specifically that would work with it, like in this case you said sodium chloride? Hydroxide? Very different. Sodium hydroxide.
You don't know it. All of those are different.
Yeah, I don't know. No. Oh, sodium chloride's salt, isn't it?
Yes, it is.
That's probably why it came up.
There's a great reference to that in The West Wing where she's really excited when she figures out that sodium chloride is table salt. But that's sort of a tangent.
So if you can have something like sodium hydroxide that mixes with the oil, it can allow the crazy weirdness of a non-polar chain that has a polar piece on it. So like at that very basic, like if you could look at it in a microscope, it'd probably look funky, right? Like especially if you compare it to the polar molecules of water and oil.
It basically looks like a long chain of something sort of like spaghetti with attached to a really, really different group of atoms. So it's a bunch of carbons and hydrogens, and at the very end, it's attached to like oxygens. Where did that come from? In a pretty unique arrangement. But it does look pretty funky if you're not used to seeing that kind of thing.
And so that is the key because it can actually allow the water and the oil to interact at that point because it has both things in it.
That is a pretty good understanding. I feel like if there are scientists listening right now and they hate me because I'm personifying or allowing the personification of atoms, that's their problem. Some scientists really hate that, but I liked what you said about, I don't hate that. I use that a lot. I liked what you said about how they were friends and there's an unequal friendship. They're still friends, they're still bonded, but it's sometimes not all friendships are the same, not all bonds are the same. So I really liked that.
Okay.
That was a great understanding of different types of bonds. Okay, so that's a good understanding of the different types of bonds. The thing that you kind of mixed up was about polar and non-polar.
Okay.
So an atom is one thing. A molecule is a group of atoms.
Yes.
So a group of atoms made up of a non-polar bond wants to interact with another group of atoms made up of a non-polar bond.
So they just like
each other.
So
it's not that oil doesn't stick together. It's that oil sticks to other oil.
Okay.
Non-polar things stick to other non-polar things. And with polar things like water likes to stick to other watery things.
Okay.
Polar likes to stick to polar. So it's like dissolves like. So like interacts with like.
Yeah. they're just not looking for each other. They're like, oh, I'm sorry, I'm looking for more water.
Yes.
And the oil's like, no, sorry, I can't. I'm actually looking for more oil.
Yeah, exactly.
Yeah,
and
okay.
then there's something that brings the two together. They don't actually interact with each other, but it's like all the non-polar tails of the soap are holding hands. So imagine a big group of non-polar people.
Okay.
So then, and then there's a big group of polar people. And there's a group of people that are half polar and half non-polar.
Okay.
So there's a group of polar people. There's a group of non-polar people. They only hold hands with others that are like them.
Okay.
So the one that's half and half polar, half non-polar, it can hold hands with all the non-polar people on its non-polar half. So imagine a ring of non-polar people surrounded by a ring of half and half people. So their non-polar half is pointing in and their polar half is pointing out.
Yeah.
Then allowing them to hold hands with polar people.
So it's almost like a converter kind of thing. We're like,
yeah.
I'm allowed to take in one type of thing on this part and another thing on this part, like a power conversion kind of thing if you travel overseas, or like, I don't know, any kind of converter like the things we're using to plug the computer into. Like,
right, exactly.
Okay, that makes sense. So then suddenly you've got this piece that allows these two things that didn't want to interact before to like interact.
Yes, it's like a nice barrier that allows these two things to interact. So now your non-polar bonds are totally covered with polar bonds, allowing the water, which is also polar, to wash them away.
Man, okay.
And now your pan is clean.
That is fascinating. And it makes a lot of sense. It actually...
A lot of science does make a lot of sense.
It's like, okay, yeah, duh. Everybody's witnessed like oil and water not mixing. And then everybody's like witnessed, oh yeah, I've got to have soap in this. It's like we know that it is coming between and allowing this thing that we need to happen, cleaning it to happen.
Yeah.
And we know it doesn't happen without it. Not just because soap smells good, but because it's like you're not going to get anywhere. You can put water all over that thing all day, and it's not going to like get it clean.
I think in my spatula is like coats it with oil because I used it on butter or whatever, and then I put a little bit of dish soap, and then it gets the squeaky feel, squeaky clean feel. Yeah.
What's funny too is that we did not at all with the same objective at all. We did an episode about soap on Podcast for Your Life, but just kind of talking about the idea of it and some of the stuff that's like, it's obviously cultural and there's like, but we had a lot of questions that we couldn't answer. Like, I think at one point one of us said something about it being just like this. I don't think we realized how manufactured it was or how much it needed to be. I was like, man, do we just find soap somewhere in the earth, and then like started realizing like, wow, you just throw this thing in there and it starts getting things clean. So
and that's one thing I don't know. I don't know how they discovered soap. I didn't look into that at all. I know that people were using soap, lye, and animal fat long before. I guess I don't know for sure. Long before.
Yeah.
I should track back and say, I assume that people figured out that you can mix lye. What they call lye is sodium hydroxide and animal fat, and make soap long before scientists figured out the intermolecular forces and everything that was going on to allow that to be possible.
Yeah.
I don't know how all that happened. I don't know for sure if you said this. I think you might have. But when you were explaining it back to me, sodium hydroxide reacts with this with the non-polar groups like the oil and stuff to make a new thing. Did you say that? At first it seemed like you thought it just like attached, but it doesn't.
So it reacts and then that forms soap.
It reacts and forms a new thing, which is soap.
Is soap. Okay, cool.
The reaction is actually called saponification.
Whoa. So that's why it's called soap.
Saponification. I actually wonder if maybe the soap came first and then saponification came after.
Got it. Okay. So here's a question.
Maybe I should have looked into the history, but that would have made this way longer, I think.
Yeah, that would make it longer. And I think there's history things, there's history podcasts, and depending on the thing, it could take so much more time. Whereas like really just explaining it, like now I'm like, whoa, every time I use soap, I'm not going to, like you said, I'm not going to be able to not think about what the chemistry is going on in my sink.
Every time you do the you'll have to remember what I just told you.
I guess it's not weird even to say that it's like a little bit like an atomic bomb, because there is an atomic thing, that's going on.
Yeah, it's all chemical reactions. Everything is chemical reactions. Your soap, atomic bomb.
Yeah.
Your real atomic bomb.
Yeah.
One's significantly more energy. Everything has atoms interacting and energy either being taken in or released. That's a broad thing to say. I'm not 100% sure I can back it up, but I'm pretty confident.
Yeah. Dang, wow. That's soap.
That's soap.
Very cool. Anything I missed or anything else I need to understand about it?
No, I think you got it. I think you understood what happens. I think you have a good understanding of soap. Okay, so we finished. That's soap. That's how soap works.
Awesome.
You learned something new today.
Yes, a lot of things, I think.
A lot of things. What was your favorite thing that you learned? Or what did you like most? What was most satisfying about this experience?
I think the way that you then explained it, like if you have people who are half polar, half non-polar, and they're holding hands, it kind of made me I'm very techie, so the idea of a converter then came to mind, and so I think that unlocked it for me a little bit more strongly.
Yeah.
And so that stood out to me as like, oh yeah, like there's a little bit of like that kind of a moment of like, okay, yeah, that makes sense.
Yeah,
So,
and that's the key. So that's the thing I hope people can take away is it's great for you to learn about bonds and everything, but if you don't understand why they impact what you're working with, then you still don't really know how the everyday application is. So I really hope that helped other people to unlock it too.
Yeah, yeah. Well, thanks everyone for joining us for the very first episode of Chemistry for Your Life.
Yeah, we've got a lot of ideas for other episodes that we want to do and other chemistry in everyday life that we want to talk about, but we also want to hear from you. So if you guys have any ideas about things that you want to hear about the chemistry of explained in your everyday life, please reach out to us. We're on Twitter and Instagram at Chem for Your Life. So that's Chem FOR Your Life. And we also are on Gmail at chemforyourlife@gmail.com. We don't have a Facebook right now. Just Jam and I both are not on Facebook, but we're working on that.
Very soon.
Very soon. So we'd love to hear from you. Please reach out and let us know what you think.
Awesome. Thanks, guys.
Thanks. This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and we'd like to give a special thanks to Autumn Kiwasong, who reviewed this episode.